Welcome. Today we're diving into the fascinating world of electrochemical cells. These devices are at the heart of many technologies we use daily, from batteries in our phones to the processes that power electric vehicles. But what exactly is an electrochemical cell? In simple terms, it's a device that converts chemical energy into electrical energy, or vice versa, through chemical reactions. This process is fundamental to modern life, and understanding it opens up a world of innovation and possibility. Let's begin our journey by exploring the basic structure and function of electrochemical cells and see how they impact everything from portable electronics to large-scale energy storage. Electrochemical cell is a device that generates electrical energy from chemical reactions or uses electrical energy to drive chemical changes. There are two main types: galvanic or voltaic cells, which produce electricity, and electrolytic cells, which use electricity to cause chemical reactions. Both types rely on the movement of electrons between two electrodes, typically called the anode and the cathode. This movement is what creates the electric current we can harness for various uses. Understanding these basics is key to grasping how electrochemical cells work in everyday applications. Let's take a closer look at the structure of a typical electrochemical cell. At its core, the cell consists of two electrodes, an anode and a cathode, immersed in an electrolyte solution. The electrodes are usually made of different materials, which allows for the necessary chemical reactions to occur. The electrolyte is a substance that conducts ions, enabling the flow of charge within the cell. A separator or salt bridge often connects the two half cells, maintaining electrical neutrality by allowing ions to move between them. This setup is crucial for the cell's operation. Every electrochemical cell, the anode and cathode, play distinct roles. The anode is where oxidation occurs, meaning it loses electrons, while the cathode is where reduction takes place, gaining those electrons. This flow of electrons from anode to cathode through an external circuit is what generates electricity. The materials chosen for each electrode are critical, as they determine the efficiency and voltage of the cell. By carefully selecting these materials, scientists can design cells for specific purposes, from powering small gadgets to storing renewable energy. Electrolyte is a vital component of any electrochemical cell. It's typically a liquid or gel that contains ions, allowing them to move freely between the anode and cathode. This movement of ions is essential for maintaining the flow of charge and completing the electrical circuit. Without a proper electrolyte, the cell wouldn't function, as the chemical reactions at the electrodes would quickly stop. Different types of electrolytes are used depending on the cell's application, ranging from simple salt solutions to complex organic compounds. Salt bridge is often used in electrochemical cells to connect the two half cells. Its main function is to maintain electrical neutrality by allowing ions to flow between the compartments. Without a salt bridge, the buildup of charge would quickly stop the cell's operation. The salt bridge typically contains a gel or solution of an inert salt, which doesn't react with the other chemicals in the cell. This simple yet ingenious component ensures that the cell can continue producing electricity smoothly and efficiently. Galvanic cells, also known as voltaic cells, are the most common type of electrochemical cell. They generate electrical energy from spontaneous chemical reactions. Everyday batteries, like those in your remote control or flashlight, are examples of galvanic cells. In these cells, the chemical reaction naturally pushes electrons from the anode to the cathode, creating a usable electric current. This process is the foundation for portable power sources and has revolutionized how we use and store energy. Unlike galvanic cells, electrolytic cells use electrical energy to drive non-spontaneous chemical reactions. These cells are essential in industries for processes like electroplating, metal refining, and water splitting. In an electrolytic cell, an external power source pushes electrons in the opposite direction, forcing chemical changes that wouldn't happen on their own. This ability to control chemical reactions with electricity has opened up countless possibilities in manufacturing and technology. Batteries are practical examples of electrochemical cells in action. Inside a battery, chemical reactions between the electrodes and electrolyte produce a steady flow of electrons, which powers your devices. When you use a battery, the chemicals inside gradually change as the cell produces electricity. Once the chemicals are used up, the battery is depleted. Rechargeable batteries can reverse these reactions, allowing the cell to be used multiple times. This simple yet powerful technology is central to our modern lifestyle. Electrochemical cells come in two main categories: primary and secondary. Primary cells, like alkaline batteries, are single-use and cannot be recharged. Once their chemicals are spent, they must be replaced. Secondary cells, such as lithium-ion or nickel-cadmium batteries, are rechargeable. They can undergo many cycles of charging and discharging, making them ideal for applications like smartphones, laptops, and electric vehicles. Understanding the difference helps you choose the right battery for your needs. The heart of every electrochemical cell is a redox reaction, a chemical process where one substance loses electron oxidation and another gains them reduction. These reactions are what drive the flow of electrons through the external circuit, generating electricity. By carefully selecting the substances involved, scientists can control the voltage and efficiency of the cell. Redox reactions are fundamental to understanding how electrochemical cells operate and why they're so versatile. Movement of electrons is what creates an electric current in an electrochemical cell. Electrons flow from the anode, where oxidation occurs, through an external wire to the cathode, where reduction takes place. This flow can be harnessed to power electronic devices, light bulbs, or even entire buildings. The external circuit is essential as it provides a path for electrons to travel and do useful work. Without this circuit, the cell's energy would go unused. Voltage, or cell potential, of an electrochemical cell is a measure of how much energy it can provide. This value depends on the materials used for the electrodes and the concentration of ions in the electrolyte. Higher voltage means more energy is available to do work. Scientists use standard electrode potentials to predict the voltage of different cell combinations, allowing them to design cells for specific applications, from tiny sensors to large power grids. Electrochemical cells are everywhere in our daily lives. They power our smartphones, laptops, watches, and even cars. Beyond consumer electronics, they're used in medical devices, backup power systems, and renewable energy storage. Their versatility and reliability make them indispensable in modern society. As technology advances, electrochemical cells continue to evolve, becoming more efficient, longer-lasting, and environmentally friendly. Fuel cells are a special type of electrochemical cell that generate electricity by combining hydrogen and oxygen, producing only water as a byproduct. This clean energy technology is gaining popularity for powering vehicles, buildings, and even spacecraft. Fuel cells are efficient, quiet, and environmentally friendly, making them a promising solution for reducing our reliance on fossil fuels and combating climate change. Solar cells, or photovoltaic cells, use electrochemical principles to convert sunlight into electricity. When light hits the cell, it excites electrons, creating a flow of current. This technology is at the forefront of renewable energy, helping to power homes, businesses, and even entire cities with clean, sustainable electricity. Advances in electrochemistry are making solar cells more efficient and affordable every year. Corrosion is a natural electrochemical process where metals deteriorate due to reactions with their environment, like rusting iron. While it's an example of electrochemistry in action, corrosion is usually undesirable, causing damage to structures, vehicles, and machinery. Understanding the electrochemical basis of corrosion helps engineers develop better materials and protective coatings to prevent costly damage and extend the lifespan of metal products. Electroplating is a process that uses electrolytic cells to deposit a thin layer of metal onto a surface. This technique is widely used to make jewelry, coins, and car parts more attractive and resistant to corrosion. By controlling the electrochemical reactions, manufacturers can create products with precise properties, combining beauty and durability. Electroplating showcases the practical power of electrochemical cells in industry. Electrorefining is another industrial application of electrochemical cells. In this process, impure metals are purified by using an electrolytic cell. The impure metal acts as the anode, and pure metal is deposited at the cathode. This method is essential for producing high-purity metals like copper and silver, which are used in electronics, wiring, and jewelry. Electrorefining ensures the materials we rely on are of the highest quality. Electrolysis of water is a classic example of an electrolytic cell in action. By passing an electric current through water, it splits into hydrogen and oxygen gases. This process is crucial for producing hydrogen fuel, which can be used in fuel cells or as a clean energy source. Electrolysis demonstrates how electrochemical cells can drive important chemical changes that benefit society and the environment. Lead-acid batteries are one of the oldest and most widely used types of electrochemical cells. They're commonly found in cars, backup power systems, and renewable energy storage. These batteries use lead and lead dioxide electrodes with a sulfuric acid electrolyte. Despite being heavy, they're reliable and can deliver high currents, making them ideal for starting engines and providing emergency power. Lithium-ion batteries are the powerhouse behind most modern portable electronics. They offer high energy density, lightweight design, and long cycle life. These batteries use lithium compounds as electrodes and are rechargeable, making them perfect for smartphones, laptops, and electric vehicles. Advances in lithium-ion technology continue to push the boundaries of what's possible in energy storage. Nickel-cadmium, NiCd, and nickel metal hydride, NiMH batteries are other important types of rechargeable electrochemical cells. NiCd batteries are durable and can deliver high currents, while NiMH batteries offer higher capacity and are more environmentally friendly. Both types are used in power tools, cameras, and hybrid vehicles, providing reliable energy for demanding applications. Solid-state batteries are an emerging technology that replaces the liquid electrolyte with a solid material. This design offers greater safety, higher energy density, and longer lifespan compared to traditional batteries. Researchers are working to overcome challenges in manufacturing and cost, but solid-state batteries hold great promise for the future of energy storage, especially in electric vehicles and portable electronics. Supercapacitors are devices that store energy electrochemically, but can release it much faster than traditional batteries. They're used in applications that require quick bursts of power, like regenerative braking in vehicles or backup power for electronics. While they can't store as much energy as batteries, their rapid charge and discharge capabilities make them valuable in many modern technologies. Widespread use of electrochemical cells has both positive and negative environmental impacts. On one hand, they enable clean energy technologies like electric vehicles and renewable energy storage. On the other, improper disposal of batteries can lead to pollution and resource waste. Recycling programs and advances in green chemistry are helping to minimize these impacts, making electrochemical cells more sustainable for the future. The story of electrochemical cells dates back to the late 18th century, with the invention of the Voltaic Pile by Alessandro Volta. This early battery demonstrated that electricity could be generated chemically, sparking a revolution in science and technology. Over the centuries, countless innovations have improved the efficiency, capacity, and safety of electrochemical cells, shaping the modern world as we know it. Alessandro Volta's invention of the Voltaic Pile in 1800 was a milestone in electrochemistry. The Voltaic Pile was the first true battery, consisting of alternating discs of zinc and copper separated by cardboard soaked in salt water. This simple device produced a steady electric current and laid the foundation for all modern batteries. Volta's work inspired generations of scientists and engineers to explore the possibilities of electrochemical energy. Daniell Cell, invented in 1836, was a significant improvement over the Voltaic Pile. It used copper and zinc electrodes with separate solutions for each, connected by a salt bridge. This design reduced problems like polarization and provided a more stable voltage, making it ideal for early telegraphs and scientific experiments. The Daniell Cell's principles are still used in modern electrochemical cells today. Today's batteries are the result of centuries of innovation. Advances in materials science, nanotechnology, and electrochemistry have led to batteries that are smaller, lighter, and more powerful than ever before. Researchers are constantly developing new chemistries and designs to meet the growing demand for portable and sustainable energy. The future of electrochemical cells looks brighter than ever. Safety is a top priority in the design and use of electrochemical cells. Overcharging, short circuits, or physical damage can lead to overheating, leaks, or even fires. Modern batteries include safety features like thermal cutoffs, pressure vents, and smart monitoring systems to prevent accidents. Proper handling, storage, and disposal are also essential for ensuring safety at home and in industry. The field of electrochemistry is rapidly evolving, with exciting trends on the horizon. Researchers are exploring new materials like graphene and solid electrolytes, aiming to create batteries that are safer, more efficient, and longer lasting. There's also a push towards sustainable and recyclable battery technologies, which will help reduce environmental impact and support the transition to renewable energy. Electrochemical cells play a vital role in medical technology. They power devices like pacemakers, hearing aids, and portable diagnostic tools. Reliable, long-lasting batteries are essential for patient safety and quality of life. Advances in miniaturization and biocompatible materials are enabling new medical applications, from implantable sensors to drug delivery systems. Electrochemical sensors use the principles of electrochemistry to detect specific chemicals in the environment or in biological samples. These sensors are used in everything from glucose meters for diabetes management to environmental monitoring devices. Their sensitivity, accuracy, and portability make them invaluable tools in healthcare, industry, and research. Electrochemical cells are crucial for powering spacecraft and satellites. They provide reliable energy in the harsh environment of space, where solar panels and batteries work together to keep systems running. Advances in battery technology have enabled longer missions and more ambitious exploration, from Mars rovers to deep space probes. Rise of portable electronics like smartphones and laptops has been made possible by advances in electrochemical cells. Lightweight, high-capacity batteries allow us to stay connected, productive, and entertained wherever we go. As devices become more powerful, the demand for better batteries continues to grow, driving further innovation in electrochemistry. Electric vehicles, EVs, rely on advanced electrochemical cells for their batteries. These batteries store large amounts of energy and deliver it efficiently to power the vehicle's motor. As EVs become more popular, the need for better, longer-lasting batteries is driving research and development. Electrochemical cells are also key to storing renewable energy from sources like solar and wind, helping to balance supply and demand on the power grid. Large-scale electrochemical cells are being used to store energy for entire cities. These grid-scale batteries help stabilize the power supply, store excess renewable energy, and provide backup during outages. Technologies like flow batteries and advanced lithium-ion systems are making it possible to integrate more renewable energy into the grid, supporting a cleaner, more reliable energy future. Despite their many advantages, electrochemical cells face challenges like limited lifespan, capacity loss over time, and safety concerns. Researchers are working to overcome these issues by developing new materials, improving manufacturing processes, and designing smarter battery management systems. Addressing these challenges is essential for unlocking the full potential of electrochemical cells. Recycling used batteries and electrochemical cells is crucial for conserving resources and protecting the environment. Modern recycling processes recover valuable metals and materials, reducing the need for mining and minimizing waste. Sustainable battery design and responsible disposal practices are key to ensuring that electrochemical cells remain a positive force for society and the planet. Education and research in electrochemistry are driving the next generation of discoveries. Universities, companies, and governments are investing in training scientists and engineers to develop better batteries, sensors, and energy systems. By fostering innovation and collaboration, we can unlock new solutions to global challenges like climate change and energy security. Career in electrochemistry offers exciting opportunities to work on cutting-edge technologies that shape the future. From developing new battery chemistries to designing medical devices and renewable energy systems, electrochemists are at the forefront of innovation. The field combines chemistry, physics, engineering, and environmental science, making it a dynamic and rewarding path for curious minds. Looking ahead, electrochemical cells will play an even greater role in our lives. As we transition to cleaner energy sources and smarter technologies, the demand for efficient, reliable, and sustainable energy storage will only grow. Ongoing research and innovation promise to make electrochemical cells safer, more powerful, and more environmentally friendly, supporting a brighter, more sustainable future for all. Sum up, electrochemical cells are remarkable devices that convert chemical energy into electrical energy, powering countless technologies in our daily lives. From simple batteries to advanced fuel cells and grid-scale storage, their impact is everywhere. Understanding how they work, their applications, and their challenges helps us appreciate the vital role they play in modern society and inspires us to continue exploring new possibilities. Thank you for joining us on this journey through the world of electrochemical cells. We hope you've gained a deeper understanding of how these fascinating devices work and why they matter. As technology continues to advance, electrochemical cells will remain at the forefront of innovation, powering our devices, vehicles, and even our dreams for a cleaner, more sustainable world. Stay curious and keep exploring the wonders of science and technology.